Hey there, welcome back to COG 376. This is Computer Models of Language Representation and Processing. We spent a lot of time recently on things like Python and programming basics of how to get strings of text and chop them up and do interesting things with them. Well, not super interesting, of course, but starting to get there. So, in general, for the course so far, we've talked about why working with text strings is this interesting piece of the puzzle, trying to treat language as just a series of symbols that can be operated on by a computer. It works well enough, but you know, this is the way that we have to represent language in a computer representation. We've also worked out a bit of how to work with text. So in Python, we've done strings and splitting and modifying them and processing and printing and looping and branching and all this good stuff. All this stays relevant, so keep it in your hearts, keep it in your fingertips as we go forward. Today, though, we're going to continue on into one of the first major tools that allows for some really powerful processing of text in the sense of trying to search out things that we know are meaningful in the text in certain patterns. So, let's jump back in to chatbots. So, we want to keep talking about chatbots, not because they are the ultimate in computer language modeling, but they are a very interesting case. They involve user input and they involve, directly interfacing with natural language. It's kind of fun with these things. And they take this human language, they do this processing, and they return human-like language back to the user. Typically, that's most of them. And to reiterate, we've already done a lot of the basic forms of this in the programming lectures so far. So just if you've been following along and you're grasping what we're doing in those kind of introductory programming sessions, then you're well on your way to being able to make a chatbot of your own. So let's look at Eliza again, my old friend, who I have done the most work with and can copy my own illustrations of. So here's Eliza. What's Eliza going to do? Eliza needs to take the input string from the person, represented in a normal string here, and then spit something back out for them to bounce off of, at least, right? Remember, Eliza's goal was to be a therapist chatbot. So what's going to happen here? Well, it's going to seize on certain words and then capture some elements of the rest of the sentence to this first one. This is a mirroring exercise Eliza is doing. It says, this person talked about themselves. I didn't find anything else interesting in their string. Maybe I can get them to say something if I just shoot this back at them. So it finds my and says, oh, then something else they said. Boyfriend made me come here. Says, your boyfriend made you come here. Again, a psychology talk therapy technique of just mirroring, just continue. I'm listening, that kind of thing. Eliza is not listening, or she is, but not especially deeply. She's listening just for surface feature text. But Eliza can also start to drill deeper on certain topics, and not terribly deep. It's not going to give amazing advice, but it will at least be able to guide the conversation towards, especially when sensitive topics come up, like depression. So here, Eliza finds the word depressed, and it also captures that, oh, this is you are depressed. And it's able to say, this is something I want to be careful with. So it's not just a straight up mirroring like the first time. It's saying, I'm sorry to hear that you're depressed. So depressed is captured, and again, you are is just along for the ride. So this is not the craziest, most difficult process to imagine. We're kind of capturing it already. We'll look at a more detailed spec of Eliza in the future, but for now, we're just seeing that all she's really doing is cutting and pasting, right? if you had a few minutes between each of these texts, you could cut and paste her algorithm and do all of this yourself inside your little room of whatever. So that's the idea. So chatbots are not doing, in a broad sense, they're not doing anything extremely complex usually. Although as we get up into the GPT-3 world, it gets, of course, quite complex. But in the basic sense, these chatter ones, these ones that kind of just blab back, they take text, they match patterns, they construct a response, and they send it, right? But the trick is that some of those middle steps are more sophisticated than they might seem at first glance. It's not, the copy pasting that you might do, you're actually doing a lot of humans' work when doing that. So how might you achieve this same kind of thing is the first question of the day. So that enters us into matching patterns of text. So do me a favor and search for the word needle on the next page. I'll give you a moment. If you're even feeling fun, just go ahead and pause it, but we'll see. Find needle. Bet you found it by now. It's there, right? Not too hard, right? All you really did was you scanned around the text. You looked at each item until you found something that matched, right? It would get a little harder if I asked you to find the word needle here. I'm not gonna wait as long on this one because it would take you some time. It's down there. That's annoying. So scanning text for humans we taper off in our willingness to do it as the size of the body of text goes up. Good God, why would we waste our time on this? But computers can do this actually super easily, right? They don't have to worry about eye movements and visual acuity and how tired or bored they are or whatever, confusing words for one another. It's just looping, right? Loop over the length of the string and check whether the word needle matches this snippet. So you've already seen all of this logic in action in the programming tutorials we've done. So, pardon. So let's look at just kind of the step-by-step visual of how a computer might solve this. So is the word name in this string? Okay, you're cheating. You already know the answer. You looked at it and you read the string and you found the word name. A computer would have to do this one step at a time. How to do it? Well, it would take the substring that we're looking for, name, and it would try to match it. Step one, is NAME the same as HI comma space? No. What about I comma space M? No. 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 Yes. It is the same. We found it. We scanned through all of the strings and we found, yes, this word does exist. This is what's known as a well-specified pattern. So when you know exactly what you're looking for, this kind of, I know the exact substring I need, that's a well-specified pattern. So Eliza might do this, say, in our first blush of understanding what she's doing. She could seize on a list of her known terms. She could just search the text for each word in her list. That would be kind of nice. Cool. That would work. It would work to be able to detect, which of these words is in this string. I found one. Now I will do things. But your patterns, there's an issue with this, and that is that these patterns are very rigid. They are not flexible at all, and you have to know exactly what you're looking for, which means that's actually not likely how any decent chatbot is going to seize on individual words. Let's do another human example. Find any phone number amid these numbers and dashes. Ready? Go. If you look carefully, you may have found my office phone number. You probably didn't have too much trouble doing that. You might have. I'm not here to judge you. Maybe you're too tired. Maybe you're not having a good eye reading day. It's fine. So, but either way, we are able to search these patterns for something that's not specified. I didn't tell you find my phone number that you have somehow memorized. Of course you don't. Who would have that memorized? I told you to find any phone number. You know the underlying structure of what a phone number looks like. You don't have to know the exact digits to understand that this pattern that we're showing right here is a phone number. That's underspecified patterns. So these are just way more useful because they allow us to match entire categories of things that are maybe more connected to each other, right? And we don't have to be completely sure of the exact form it'll take. And also the word underspecified, don't take that to be like, oh, it's underperforming or something. No, these are actually far more powerful than a very rigid pattern. So the idea that a lot of things that have a similar shape often have a lot of things in common. Like, for example, all the different forms that the concept of depression can take, right? Someone might say the word depression. They might say depressed, depressing, depressive, all of these things. Anxiety, they might say anxiety or anxious, right? And they're touching on the same ideas and topics, but they are all connected. So you might want to be able to find patterns in text as opposed to raw specific substrings. So ELIZA is way more likely to be matching a set of related patterns to give a similar response. Any of these words might trigger ELIZA to say something like, I'm sorry to hear that you're feeling X, right? Because that makes sense. That makes sense for what the goal of the conversation is. So, but what it comes down to is we're trying to talk about how these kinds of things work, how they are implemented. So how did you do your phone number trick? Let's look again. I've re-randomized the array of numbers. And let's just try to pay attention to how you are solving this. I'll give you a few beats to just like run through it, but really slow yourself down a little bit and pay attention. What are you attending to? What are you looking at? What are you stopping on? Just give it a tick. So here we go, another block. You may have found it by now, but we won't highlight it until the end. How are you doing this? What are you using to jump around here? Because this isn't like the needle in the haystack example. You have lots of stuff you can use to solve this question. You have the dashes. Those are good. Those help us break things up. That's super useful. We have not just the dashes, but we have an understanding of, well, aren't just long strings of numbers in phone numbers. They're broken up in a certain range of sizes. So we can get rid of all of the things that are just way too large right away, okay? Now, you might not be doing this all at once, but these are the ways that you might be breaking up the information. So now if we just look at, well, if I arrange things in terms of how long they are, I can color the 4 length digits different from the 3 length, 2 length, and 1 length ones. Now we have this idea of there's only one of these patterns that makes a valid phone number, is this one. So that's a pretty complex take compared to searching for the word needle in the haystack of words. You did more steps. Now, it may not be that you did those literal exact steps, but this is the idea of this is a sort of a humanish way to search for the phone number. So let's recap it. Use the dashes to kind of break your scanning up into chunks. So if nothing else, you can at least jump from dash to dash and say, what's on either side of this, right? Find the substrings that are like of the appropriate length. You know, the ones and twos you might want for country codes, but the threes and fours are the real key. And then once you find a pattern that goes 334 in terms of the number of digits, maybe the extra one, you're done. You found the phone number. Computers just do this with regular expressions. Welcome to regular expressions. Also known as regex, they are excellent. They are a powerful tool, regular as in rule-based, and expressions as in patterns, right? So it is a way of building an expression of like a rule-based pattern that will then run wild on your text and find things for you. Pull things out that are useful, right? The only useful thing in that string of random numbers I just threw at you was my office phone number. That was a thing you were able to search for because you knew some of the rules of how phone numbers do. So, it's a way to programmatically define what a given pattern of text looks like. So you can use it to locate patterns, you can capture and return pieces of the patterns for later use, you can delete and replace things in these patterns. In fact, this is how you might end up using this in normal life. So where might you see regex? The cool thing about regex is that it's what's known as a formal grammar, and it's designed to create these little rules for parsing strings of text. The thing that's very cool here is we've chosen Python for this class, right? That's the place we're going to play around in our code. Independent of any programming language, regex lives in all of them, more or less. Nearly every language is going to implement it in a very similar way. There will be slight differences, but the concepts that we're going to cover here are transferable across any language. So, including, not even really language, but into things like the text editors, the search and replace functions in Word and Notepad, like I said. So, the point I'm trying to make is, if you learn this once, or at least, you know, get passingly familiar the first time, and then next time you'll relearn it, and you'll relearn it, of course, right? But the idea is that once you understand how regex works, you can use it anywhere. This is one of those things that, you know, it's a practical, important thing to talk about with programming, because some things feel like you're kind of pigeonholing yourself. I want you to understand that regex is not pigeonholing. It is very broad if you understand how this search process works. So I'll stop plugging for what I hope you want to learn and carry us into what the heck is this stuff. So, what are the features of a regular expression? There's a few, and there's kind of more than this, but just to give you a kind of lay of the land, right? First is the delimiter, what captures a regular expression. So any regular expression is going to be between two 4 slashes. Yes, the one leaning right is 4. That's a common misunderstanding from people. So they move the same way that the text is moving, right? Forward slash. So between two 4 slashes is where you would find, or rather where typically you would, it would be hard to mistake this for non-regular expressions. This is sort of the universal way to write it. You don't always have to use it when you're doing when you are calling a function to perform a regular expression for you, like in Python. You might not need the slashes, but this is just the way we will write them when we're talking about them, okay? So what else can we do? We can match literal characters, so exact letters, kind of, you know, the well-specified parts of our strings. Like A and B and all these things. But there's also lots of meta characters. So these are helper characters that aren't going to be recognized as literal characters, but they'll be things like, help me find multiple of this, or at the beginning of the string, do this, or etc. And then there's also a few escape sequences. So things that, letters that have a backslash before them that represent categories of characters, or special characters, or things like that. You don't have to focus on all this. We will dig right in. So, how can we represent characters in regex? Well, if we're just doing basic, super simple character search, then regex is kind of the same as that extremely dumb search we did for finding the name in the string, right? It was just look at this one, look at this one, look at this one, right? That's what a regex regular expression composed entirely of just normal characters is going to do. So this first one, A, this search would essentially say match if there's an A anywhere in the string, go grab it, right? AB, on the other hand, would find the letters A and B right next to each other, and they'd have to be together, right? Depress. This is find the exact sequence, depress, right? So, simple enough so far. This is where we break from simple and get into fancy. So, more powerful functionality comes from these meta characters. We will, I'm sure you're in the dark for now, don't worry, we will expand into the light. So, meta characters are these characters that won't be recognized as literal characters, literal letters. And in fact, if you want to use them, you have to use a special meta character to denote that. Instead, you use them to serve a special function when you're building out the pattern. And this is where the flexibility starts to come in. So, let's look at a few useful regex meta characters. Top to bottom, okay? Follow along, top to bottom. The dot. The dot means, I've thrown in like this sort of one-word concept for, well, not one word for all of them, but short concept of, the dot means any. This means any character, the dot can fill in for any one character, okay? The caret and the dollar sign, these are start and end symbols. So if we put these in our regular expression, we can say this has to happen at the start of the string, or it has to happen at the end of the string that I'm searching. Now, the question is things like, does this file begin with this? That's what you can use that for. So you run your regular expression on 25 files, and you find out which ones start with, call me Ishmael, right? And hey, there's Moby Dick. So that's another meta character that's useful. We have, there's a handful now that do kind of a similar kind of thing. These all operate on the character that came before them. The question mark is the optional concept. And that's the idea, you can find whatever letter came before this special character. It's okay for there to be one there, or there could be not one there. It's optional. It's okay for it to be there or not. The plus means one or more. So one or more of a number of letters in a row, right? We'll do some examples in a minute. I just want to get these down. So plus means like whatever character came before, do one or more of it. Rather, match one or more. So it could be, if it was the letters A and plus, that would be at least one A has to be here for this to match, but there could be a million A's, and it's fine, as long as they're all together. The asterisk combines those first two. So it's sort of, there could be nothing here, or there could be one or more of the thing here. That's a little bit abstract. We'll show it off in a minute. We also have a few more that are pretty important in a general sense, but we'll work through them soon. You can define your own class of characters. So, for instance, the dot means any character, right? Well, the brackets mean you can specify a set of characters that are allowed to match. So, helps you to match things that could all work together. Group is kind of, you're creating a sub-expression. You'll often just use this to, match a very explicit string, just normal letters. But it has all kinds of other powers that we'll talk about in a future lecture. It's pretty important. Repeat. This is the idea that you can repeat whatever character came before many times. You can repeat, say, 5 times or in a range, so 2 to 4 times. So we want to see this character, but not too much of it, right? The pipe. This is the or idea. So this means that anything on either side of this pipe is allowed. Yeah, so okay, it's too abstract. The escape character is the last one, and this one is actually pretty important to know. Escape character says, "Hey, we've got all these magical special meta characters. If you want to actually use one of those in the normal text, I can do an escape character and then a period if you want to match the period, so that we actually capture the actual period." Let's look at examples. We can always come back. So A plus, what does that mean? Well, that's the grade you hope to get, blah, blah, blah. But what does that mean? That means any string, any piece of this string where there's at least one A, but any number of them in a row, right? So in this case, we have A would match for sure. AA would match, AAAA would match, AAAAA would match. These are all the pieces of the string that would match. So if I had a string that had any number of letters in it, any number of words and such, as long as it contained at least one sequence of A's of length 1 or more, then it would match. Okay, next. AB plus. Okay, now you might initially think this means, oh, well, I'll match AB, AB, AB over and over. Not so. Remember, these plus operators only work on the very previous, the next character, the character next to it, the previous character. So this one says, find any number of B's, as long as there's at least one, in the same way, but it has to start with an A. So AB would match, ABB would match, etc. Okay, let's keep going. Let's keep permuting. Let's keep doing slight variations on this. This one says, find one or more repeated patterns of AB in a row. Okay, so AB, that works. AB, AB, that works. Because what we've done is we have treated AB as a single group. We have grouped it in the parentheses so that now the plus sign works on that group, not just one letter. So abababab, abababababab, all these work. Let's do another one. A plus B asterisk. Okay, so any substring that starts with at least one A and then could have B's or it could not have B's. It doesn't matter. It's okay either way. So A, that works because there's at least one A and there's no B's, but that's okay. B's were optional. AB, that works. ABB, AAB, AAA, AAA, all of these work. I hope the pattern is starting to make sense there. Then we finally have, this one's actually pretty critical to a lot of the things you might do in this world, so I made sure to include it. A or B. You can just think of that pipe as or, the concept. So this says a string that has A in it, that'll match. And a string that has B in it will also match. They're both okay. It's acceptable to do both. A or B. Okay. So, whoa, we've looked at a bunch of meta characters. Let's talk about what kinds of characters these are, what kinds of operations we're doing. Kind of lump some things together to make it less confounding. So one category of things we're doing, of patterns we're able to match in this regular expression world is quantifiers. So this is the ways we're indicating some amount of a given character or subsequence that we're looking for. So, for example, the optional question mark character says X can either be there or not. It's fine either way. So 0 or 1. X plus means any number of X's, as long as there's at least one. Then we have X star again. So either no X is fine or as many as we want. This one seems like, okay, why are we specifying this? Sometimes it helps to be able to account for something that could be there, but not just anything, right? We are only accounting for the presence or absence of one kind of thing. Okay, continuing. We can also specify an exact number of times. So X needs to happen exactly n times within these curly brackets. that's a quantifier for x within those brackets. You can also do at least n times, so give a comma, but don't specify the upper bound, so n or more times, and then x n comma n means at least n times, but no more than m times. Okay, this is good. This is the ways that we can say, hey, repeat this a certain number of times. We'll start to see why this is powerful soon, because we're going to start combining it with things like character classes. So, character classes, these are let us match a variety of possible relevant characters as opposed to just one explicit character, right? So you can create your own set, your own class using the box notation, the brackets, square brackets. And we could use predefined ones that are very common in processing lots of text using escape sequences. Let's look at the list. So once again, one character class that captures everything is the dot, right? Any character. That's cool. That works. This helps us to just say, hey, there's going to be a character here. I don't care what it is. I still want you to match the pattern. Then we have a basic character class that says A, B, C. That says either A, B, or C. Any of those are a valid thing for this position in the pattern. We also have not A, B, C, which is basically saying that that starting caret says not these, so everything but A, B, and C. So it'll match on anything that's not those, right? You can also do a range. You can say match the range of characters between lowercase a and lowercase z. Now, I say lowercase specifically because those in the Unicode world, those things are next to each other. Not always the case when you're saying, say, A to capital Z, for example. But that's the idea. You are saying, hey, any of these. So the dash inside of the character class means anything between these two values. We also have a bunch that are predefined, and these are the ones that are nice, clean, human-readable concepts. So \D, so it's an escape character. If you did it without the backslash, it would just match the letter D, lowercase, right? But with the backslash lowercase d, that says it's sort of a shorthand for any digit character. So anything from 0 to 9. \D is any non-digit, so the opposite case, the complement to that. We also have white space. You don't have to think too deeply about what's in there. The \T means tab, \N means new line, \XOB, I've actually forgotten. It's one of the special characters it's mostly the things that help you, arrange text. R is the carriage return, the Windows version. Yeah, so white space, things that are not meant to be read especially, but are still present in the string because they help render it and separate it, right? Even just normal space characters. Oh, that may be what the XOB is. Yeah, that seems familiar. Okay, so space. \S is, again, the opposite, the complement. And then \W is word characters. So things you're going to see in normal words, A to Z, capital A to Z, underscore, and 0 to 9. You don't see underscore that much, but in variables, etc. This is a list. This is all a list of character classes. So what's the point of this? Well, it's a way to really quickly capture a subset of all of the Unicode characters that you might have available. For example, given the huge range of Unicode characters that exist and how they're kind of scattered everywhere, it's quite nice to be able to capture this subset that of all the relevant word-like characters that we have in English text using just this escape sequence. So keep that in mind. Now, let's work through a couple of examples of this. We've covered a lot of tedious details. Let's watch how they work when we're trying to apply them. So let's put them to work. Let's revisit our very first one. How might I write a little algorithm to match a phone number? Or not algorithm, I mean it is an algorithm, but a regular expression that will algorithmically match a phone number. So a phone number. What are the parts? Well, we know that the first number and the dash, those are at least optional. So we'll need to consider that. Our friend, the question mark character, might come into play. And then the rest is all very specifically defined. It's pretty rigid. It's exactly 3 numbers, and then 4 numbers, separated by these dashes. Now, before we get started, there's a lot of different ways you can formulate this. We'll even cover 2 right now that will actually do the same thing and capture things correctly. But it's absolutely a science, but there's an art to how you arrive at the answer that you want. So, regular expression. Let's begin. Open it with our opening slash, the /. So what's the first part? We know that the first digit is optional with its dash. So we can group that digit into a little section with its dash and then give it an optional operator, right? So the quantifier question mark says, I don't know if this is going to be here or not. It doesn't necessarily matter. Okay, cool. So that will either get captured or it won't, and that's fine. Then we have to have exactly 3 characters and then a dash, right? Well, we know how to do exactly some number. That's \d 3 times, right? The 3 operator, the bracket. And then we have a dash. Hey, and then we do that again. \d3 again. And then we have what's left? 4 digits, right? So we'll just do \d4. Hey, I think that'll work. Let's cover it again real quick. We've got the optional first digit with its dash. That's optional because it's grouped, and we have operated the question mark operator on it. Then we have exactly 3 digits, a dash, exactly 3 digits, a dash, and then exactly 4 digits. That is our regular expression. This is exactly how you would write it. It's horrible to look at, but now that you're starting to, I hope, understand what the pieces mean, it won't be totally off-putting. So I said there are multiple ways to do it. We can do this in an even dumber way because we know the exact shape of these letters, of these digits in the phone number, but we don't necessarily know what the digits are. Okay, so we can do this in a very, very simple way. Open a bracket. We have an optional digit, an optional dash. We have 3 digits, a dash, 3 digits, a dash, 4 digits, and then slash. And there it is. That's not very elegant, but it will do the job. Actually, there's an error in there. I'm just realizing, and I'll leave it up to you to figure out. What have I done wrong with the optionals that would maybe make this pattern match some things that it shouldn't? Okay, so let's do another one. What if we were trying to find text files with a particular form, right? So whatever name of the text file, who cares? But it's any letters that would indicate a name. 2 digits and then .txt. Ooh, we've got a dot in there now. That's a little funky. How do we, because dot we know means any character. How do we get here? So let's break it down a bit. So first, one thing about text files, or rather file names that we're going to understand here is they're going to be complete strings. We don't want things to come before them. We don't want things to come after them. So, we don't want to have this particular format screwed up by having a million other things come before it. We know it's this exact shape. So we'll begin with the start symbol because we don't want anything else to come before this exact pattern, right? Then we have a series of word characters. So any number of word characters in a row, but there's got to be at least one. Otherwise, it's not really adhering to this pattern. Or at least that's what I'm saying is the intended structure of this, right? So there's at least one word character, but any number of them, who cares? Then we need exactly 2 digits. And then we need just the extension .txt. We're not looking for other kinds of files. And then finally, we need the end symbol because we want to make sure nothing comes after it either. Not txt dot other stuff, right? So let's build a regex. Okay, so we're going to open the brace, or the slash, start symbol, so that's the caret. We have any number of word characters. What is any number at least one? Well, that's going to be the /w and the plus, because plus means at least one of these things. And then we're going to have 2 digits exactly. And we can do that 2 ways. This time we're just going to go the simple way because it actually saves typing. /d/d. And then, ooh, we need .txt. Do we remember how to do a dot? The escape character, right? If we do a normal dot, it won't match, or it'll match anything, right? We could have whatever name, number, txt. That's not going to fly. So we need the escape character for the dot, and then the letters txt. And then finally, we do the end symbol, and we close the regex. And there it is, the regular expression that describes this kind of file name. This is the kind of thing you could do if you were searching your computer. If you figured out how to get the regular expression engine running on your operating system, it exists. It's called grep. You can look into it. This is how you would write something. You'd say, find me all the files of this particular shape, or any shape that you understand, right? This is a way to extract meaning from the ether. So let's do another one, hoping we're not beating this dead horse. Web domains. Okay, so what do we know about web domains? Basic ones, right? We're not getting into the fancy stuff and the .xyz's and the cs.pi.oswego. Blah, 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 right? Let's do some basic ones. So what do we know? We know that the www at the front is actually usually optional. You don't really have to type that, because usually it'll just automatically redirect you there anyway if it exists. Whatever the domain name is, we don't know that. In fact, we don't care. We're trying to get all the ones that exist, right? And then there's a handful of top-level domains that are useful, right? So these are the coms, the orgs, the govs, the nets, that kind of stuff. So, given all that, how do we construct this regex? Open. Okay, the www is optional, and its dot is optional along with it. So, how do we make it that optional? Well, we've seen it before. You put them in a group, and then you put a question mark at the end, right? www /dot, because we have to escape it, right? Otherwise, that dot will match anything. So www /dot, all in a group, optional. It is an optional part of the string. Then we have the domain its name, right? Well, that is going to be word characters only. We're not going to allow other kinds of characters to get in there. But there's actually an issue. If we recall, the \w class includes A through Z, capital A through Z, 0 through 9, and the underscore character. But that's actually not allowed in web domains. Something that is allowed is the dash, the hyphen character. You're allowed to hyphenate. So that means we're going to have to construct our own custom character class that is the acceptable characters for domain names. Let's do it. We know A through Z, that's fine, lowercase, and capital, 0 through 9, those all work, and then we need the dash. So that's going to be bracket, A through Z, 0 through 9, and we're going to have to escape character out the dash because, as we've just written, the dashes inside these mean something else. So we need to make sure, hey, I actually want this dash character to be one of the ones that we are looking for. And then at the end of this segment, I happen to know that domain names can't be less than 3 letters long. You have to have at least 3 or at least last I checked, right? So let's presume that's true. We could have just used a plus if we needed at least 1 character, but that's not how domains are allocated. You can't have a single character domain. So this indicates we need at least 3 or more, right? So 3, comma, unbounded. Who knows how many? It's all fine. Okay, so what do we need next? We need a dot to separate the domain from the rest. Okay, we got our dot, backslash dot to say, hey, make sure this is an actual dot, actual period. And then we can select from a set that we know the set of com, org, gov, and net. So com, or org, or gov, or net in this group. And we end it. That is our regular expression to capture website names. You could actually even have the start and end characters in here if you wanted. That ultimately ends up being more about what exactly are you trying to accomplish. Sometimes you want to make sure, and sometimes you don't care. So either way works. Okay, so I hope I'm tiring you out a little bit with examples, but I really want you to understand, just down to the nitty-gritty, how these, what looks like an extremely complex string at the end here, is actually just a bundle of smaller concepts that help us match different kinds of strings. Let's go through another larger one, but we won't dwell here. This, what do we think this is? Well, let's break it down. We start the what's the word? The expression, the regular expression. We immediately start with a character class. So anything that comes in here. So this can be word characters, the period, the underscore, the percent, the plus or the minus, the dash. You're supposed to backslash out the dash, but sometimes it's able to figure it out. Be careful yourself. Okay, so that's a character class we've defined. Okay. There's and we need any number of those as long as there's at least one. We need the @ symbol, specifically the actual @ symbol. This is not a special character. That just means the @ symbol is here. Okay, we open up another character class. Words, dots, and dashes are all good. Plus, so that's any number plus 1, or any number of these at least 1. We have a period, backslash period. We know what that means. Match a single period. And then we have at the end anything, so any letters, so A through Z, lowercase or capital, and then between 2 and 4. So at least 2, no more than 4 times. What do we think this is? One wild guess right off the bat might be, is this a web domain one, just like we did? Google. Well, let's kind of walk through. Remembering that we're going kind of left to right, what's going to match? Well, this one's actually all going to get caught in just that first character class, because all of the letters in this string match in just that first category on the left. W's are there, periods are there. So word characters and periods, any number plus at least 1. There's never an @ symbol, so we can't match that. This fails. You might be glomming on to the idea that the @ symbol is important. So let's do an email address. john.linstead@oswego.edu. Well, john.linstead follows the same rules. It's letters and dots. We have our @ symbol. We have letters and dashes and dots for Oswego. We have a bespoke dot that we must have, and then we have 3 letters, which is between 2 and 4. They're all normal letters. This matches. This was a regular expression to create, or to pattern match on email addresses. Okay, let's get through this. I would normally chop this up, but I think that we can just nail it out. So, one last thing that you might want to know that is available in the toolkit, right? You can look it up later as it becomes relevant. But you can also match based on the boundaries of things. So, things that are explicitly outside the pattern. So, we've seen the beginning of the string, the end of the string, right? those boundaries. But there's also the \b, which says any series of non-word characters, find one of those and put it here. So, and then \B is the opposite, of course. And then there's even this trick you can pull where you can be self-referential. You can say, find from the end of the last time this pattern matched. So if you're matching multiple patterns in one string, start there, which is interesting. It's a little bit recursive. It's a little tricky, but it's something to have. So before we exit this, let's revisit Eliza. What's Eliza doing? Eliza, in this particular case, is trying to find any prefixes of a list of medical terms and then use that as a way to say some relevant thing back, right? So it's going to look up if a term is found, which it will have to search for, it'll look it up and then it'll find responses, right? So let's run through that. What are we looking for exactly in terms of a regular expression? We're looking for any any number of terms from a set of medical terms that we're keeping track of because we are a therapy bot. It can be partial, so it's just the prefixes of those words. We need to consider that when we're constructing this. And then it can be anywhere in the string. We're not concerned about it being at the start or end of the string. Okay, so what does that come down to? We've got a term prefix. There's multiple possibilities for that, right? So that might be an or. We're have a pipe action. We're gonna have some ors. And then any number of other letters until the word boundary. Okay, I think we can do this. So also, there's going to be no start or end symbol because we don't care about the position. And that takes us there. Okay, so begin the regular expression. Open it up. We're only going to do the two that are written here. You would presumably have a list that would help you match. But for here, we have both depress and angzy as the prefixes, right? Okay, so those are a category. And they must be there somewhere for this to make any sense. So we're not going to do any optional or anything. This is just, here's a set that are available. Okay. We also need then any number of other characters. We don't care about the rest of the string. It needs to be there, right? And very specifically, we're targeting the word, right? So we don't care what letters come after D-E-P-R-E-S-S. I mean, they could write random gobbledygook, but really the odds are good they're going to write the rest of any one of these words. So all the other letters that might come after that, and specifically the word letters. And then, how do we know the word has ended? We need it to end to make sure it's a word and not just random smashing on the keyboard. A word boundary. End it. That's our regex. That is, find any of these terms, depression or anxiety, and these are the prefixes, so finish the word with the W, and then find the word boundary with B. This is a regular expression that can capture something that's in that sentence. Aha. So, this is one of the ways that Eliza can dig in and pull something out. Now, the trick here is that all we've talked about so far is finding patterns using regex. But as we've already seen, Eliza needs to figure out what to say next, so she needs a couple of things. She needs to know which term it actually found. Just because something matched doesn't mean it's a specific one, right? It needs to figure out, I need to look up which way I'm going to address this, right? And then other parts of the user sentence it's going to use. We've already seen that it's able to do this mirroring thing. So it's, my boyfriend made me come here. Oh, your boyfriend made you come here, right? So that's what we'll get into next. And before I leave, something that you should go play around with, just because it's fun, honestly. If you want to solidify your understanding of this particular lecture and this content, go to regex101.com. It's this best tool I've ever seen for experimenting with regex. and it has even has this beautiful panel in the upper right that explains to you in human words what each part of your regular expression is doing. And it highlights where things are matching. It shows you what is returned. It's really good. Give it a try. Keep it on hand too. I'll even put it on my website when you start to use regular expressions going forward. So here's a clip of the website, an image. It's just really great. You can see how I've constructed this ABC match that must come at the end of the sentence. And we see A something, B something, C, that matched. It explains every bit of it. It's great. Just go play with it. Okay, as always, even though we've run a little long, I'll leave you with a final thought. Think about the phone number matching task from earlier. Compare the humanish algorithm, or your own observations on how you did it, to the way a regular expression would achieve something similar. What is there in common? And what differs? Why might that be? All right, thanks. Take care.